Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Centrifugal Separations. Previously in one of the lectures we have already seen the centrifugal force, particle settling under centrifugal field, those kind of things we have seen, and then compared with the particle settling in a gravity field, right. So, then there we have found that the magnitude of a centrifugal force is several hundred or sometimes even several thousand times higher than the gravitational force. So, some particles, if you wanted to separate from solid fluid system, if some particles taking very long time to settle and being separated out under gravity field, then that is not going to be practically possible, right, or you may not wish to wait for so long for those particles to be settled under gravity and then you separate and then you go for the subsequent operation. So, that is not possible always, right. So, under such conditions, if you apply kind of centrifugal field for separation of those particles, then the separation is going to be taken place in very less time, because the magnitude of centrifugal force is in general much higher than the gravitational force, several times, like 100 times or 1000 times, depending on the rotational speed of the centrifugal ball that we are using. That is one advantage. Another advantage is like that, in general gravitational sedimentation equipment or very big size tanks or containers or kind of things are used for gravity separations. But centrifugal separation can be done in a kind of small balls having diameter 700 to 1200 diameter only. So, such is the advantage. So, because of these two major advantages of centrifugal field, in general separation based on the centrifugal field is going to be advantageous as well as the economical over gravity separation, especially if the separation or the settling velocity of the particle is very small in general, right. So, now we see why centrifugal separations are required. As I mentioned, wide range of industrial applications are existing where centrifugal force is used in place of gravitational force to accelerate separations. The acceleration of separation can be done by using these centrifugal forces. Acceleration of separation can be several thousand times compared to gravity. Some benefits include far greater rates of separation, that is possibility of achieving separations which are either not practically feasible or actually impossible in the gravitational field. Some particles, let us say if you have a very fine micron size or sub-micron size particles are suspended in air, and then if you wanted to pure that air, gravity separation if you are doing try to do, that is going to take long time, very long time, or sometimes it is not even possible, right. So, but if you apply centrifugal field for such cases, it is easy that acceleration of separation would be taking place, and then under the centrifugal field the separation of those particles can be easily done as done in sometimes in cyclone separators, etc. And then substantial reduction of size of the equipment is possible by using centrifugal field in place of gravity separation, as I already mentioned. Then how to generate centrifugal field? Having seen that advantage of centrifugal force, now next point is that how to generate centrifugal field. There are two different ways are possible in general. First way is that by introducing a fluid with a high tangential velocity into a cylindrical or conical vessel, as we do in general in hydrocyclones or cyclone separators, right. So, let us say what we have in general cyclone separators or hydrocyclone separators are something like conical shape, something like this. So, the fluid that comes in, that are the fluid that is containing the particles, fine particles, they come at high velocity and then hit the wall. So, then they are kind of spiral of this rotation of this the fluid element will take place, and then when they are hitting at high velocity to the surface of the cone, and then cone radius is size of the cone, I mean the cross section of the cone decreases gradually downward. So, then because of that one a kind of rotation, increased rotation of the fluid element will take place, and then that will generate a kind of centrifugation, and then particles will be settled from the bottom, settled at the bottom and collected here, whereas the clear air can be collected from the top. That is what we do. This is one way of doing the generating the centrifugal field. So, here at any point what you see, you have a kind of two forces. One is the gravitational force that is acting downward in the y direction, and then another one is the centrifugal force that is acting in the radial direction. So, if fluid is rotating, then in vertical direction gravity is predominant. So, dP by dr should be nothing but minus rho g or minus g by capital V. We can write V is a kind of volume per unit mass kind of units. And in horizontal axis, what we have? We have centrifugal force predominating, which with pressure drop dP by dr is nothing but rho r omega square, that can be written rho u square by r as well. So, this dP by dr is equals to rho r omega square, that again anyway we are going to derive in subsequent slides. And then larger and heavier particles will be collected near walls, and then smaller and lighter particles will be taken off through the outlet near the axis of a vessel. The second approach is by use of centrifuge. In this case, what happened? Fluid is introduced into some type of rotating ball and is being rapidly accelerated. You take a ball, in that ball you take this fluid containing particles, right, and then rotate that ball at very high rotational speeds. Then what happens? Heavier phase will be thrown towards the wall of the container ball, and then will be taken away, separated from the other phase, okay, lighter phase. So, that is what the other way of inducing the centrifuge. So, because of frictional drag within the fluid ensures that there is a very little rational slip or relative motion between fluid layers within the ball, and all the fluid tends to rotate at a constant angular velocity. Okay, these are the two ways that we can apply to generate centrifugal field in general. Now, the areas applications, there are large number of applications are available for the centrifugal separations or the separation by using centrifugal field. So, separation of particles on the basis of their size and density in one, and then separation of immiscible liquids of different densities. Sometimes there may be immiscible liquids, let us say from oil industry, from vegetable seeds, edible oils, when you produce, there are a kind of two phases, aqueous phase and oil phase in general. So, these two phases are immiscible and their densities are very close to each other. So, separating those two phases is a kind of very difficult task by gravity, or it will take a long time. So, if you apply centrifugal field, so then those immiscible liquids of different densities but close to each other, the densities are different but close to each other. So, those separation, those immiscible liquids can be separated easily. Then filtration of suspensions, already we have seen in one of the previous lecture, centrifugal filtrations that are quite famously used, and then drying of solids and crystals. In those centrifugal filtration, we have also seen, like sometimes if you want to partially dry the solids that have been separated from the slurry, then you rotate those solids in the same centrifugal separation unit for a very large, for some more time, but very high rotational speed compared to the rotational speed of filtration separation, or the separation of the slurry when taken, whatever the rotational speed you have given, compared to that one you have to rotate at much very high velocity. Then whatever the liquid that is there between the particles of the cake, or trapped between the particles of cake, that is interstitial spaces of the particles in the cake are being occupied by the liquid, those liquid also be drained off, and then solids would be partially dried. So, drying of solids and crystals is one application. And then in one of the previous lecture also we have seen emulsions and colloidal suspensions. So, they in general agglomerate. You wanted to make a kind of uniform solution, then breaking down of emulsions and colloidal suspensions can be done by this centrifugal field. And then sometime for separation of gases, especially nuclear industries where isotopes are of this close density to each other. Then some of the other areas are centrifugal packed beds, where you can find this application of centrifugal separations. Now, shape of free surface of liquid under centrifugal force. Right, we all know that when in a ball, if you take a fluid and then rotate it, the interface will have a kind of paraboloid kind of shape. Right, if you rotate it much higher speeds, then it will be, the liquid would be a kind of attached layer to the walls of the container, and then almost the bottom of the surface is ball is a kind of a vacant kind of thing. That is, let us say if you have a kind of centrifugal ball here, initially you take a liquid, and then you rotate. You rotate at certain velocity. So, when you are rotating at moderate rotational speeds, then interface will have a kind of paraboloid shape like this, right. So, when you rotate at very high speeds, then what happens, these liquids may form a kind of almost two different layers. So, they are only liquids, the whichever liquid is being rotated is under centrifugal field, and then centrifugal field, if it is strong by large rotational speeds, these liquids are attached to the wall as a kind of cylindrical layer like this, where leaving this bottom without any liquid, almost kind of dry bottom you can see here. So, these kind of things in general we know, but can we generate or develop a kind of equation for this thing, that we are going to see now. Consider an element of liquid in a centrifugal ball. Ball is rotating at angular velocity omega. So, the centrifugal acceleration is nothing but r omega square. Then ratio between centrifugal and gravitational acceleration is simply r omega square by g. This is also we know. This ratio is measure of separating effect obtained in a centrifuge relative to that from the gravitational effect. This ratio may be very high, up to 10 power 4 in some industrial centrifuges, and can be still more than this order of magnitude in the ultra centrifuges as well. In practice, this axis of rotation may be vertical, horizontal or intermediate, but whether the axis of rotation should be vertical, horizontal or intermediate, that depends on the applications. Now, let us say you have taken a centrifugal ball, right, and then you rotated it a kind of a moderate speed, not very high speed, so that both gravitational and centrifugal forces are of comparable magnitudes, right. So, this radius of this paraboloid is r naught, and then it is rotating by along this axis, vertical axis z naught at this location, right. So, let us say at any point on this paraboloid, if you wanted to find out the relative magnitude of these centrifugal and gravity forces, what you can do, you can draw a kind of tangent like this, right. So, that there you what you do, you for that tangent you try to get the normal components like this. One is in the downward direction where the gravity is predominating, another one is a kind of in the horizontal direction where the centrifugal field is dominating. If you take the resultant of these two vectors, summation of these two, then that resultant whatever is there, that is going to be the total force that is acting at that particular point where you have drawn the tangent, right. Figure shows an element of free surface of a liquid in a ball. Ball is rotating at radius r naught about vertical axis at very low speed, so that the centrifugal and gravity fields will be of same order of magnitude. Centrifugal and gravity forces are perpendicular to each other and may be combined as shown below here to give a resultant force at equilibrium, which must be at right angles to the free surface. So, this resultant whatever is there, that is at the right angle. So, if this is a kind of tangent, at this point of tangent, if you have a this right angle at triangle, if you draw a line, so that is going to give the resultant of these two, okay, which is nothing but summation of these two, r and r omega square and g. Thus, the slope at this point is given by dz naught by dr naught, obviously the slope, right, that slope at that point, whatever the tangent that you have drawn, that slope, this tangent at this point, if you draw the slope, then what you have dz naught by dr naught, dz naught by dr naught, right. So, that is dz naught by dr naught is equals to radial component of force divided by the axial component of force, that is nothing but r omega square by g, okay, where z naught is axial coordinate of free surface of the liquid. Integration of the above equation will give us z naught is equals to omega square r naught square by 2g plus a constant. Then let Z naught is equals to ZA at R naught is equals to 0, that is ZA is value of Z naught which corresponds to the position where the free surface is at axis of rotation, that is at R naught is equals to 0. Then in this equation if you substitute R naught is equals to 0, then constant is going to be Z naught is equals to ZA, that at R naught the boundary condition is what? At R naught is equals to 0, we have Z naught is equals to ZA. So, this when you substitute here in this equation, you will get constant is equals to ZA, and then we substitute here and then simplify, you can write this equation as Z naught minus ZA is equals to omega square R naught square by 2G. This is the equation that represents the free surface of fluid layer which is under a centrifugal action. Okay. So, let us take base of ball as the origin for the measurement of Z naught, and then if positive values of ZA correspond to conditions where the whole of the bottom of the ball is covered by liquid. So, as I mentioned, like different speeds, if you do this rotations kind of thing, right, if you do a kind of a rotation at smaller flow rates, if you rotate this ball at lower angular velocity, so then you can have a kind of interface something like this, right. So, this is all a kind of liquid. So, the whole of the bottom of this ball is covered by the liquid. So, under such conditions in general whatever the ZA that is you get is going to be a kind of a positive one. If you have a kind of negative values of ZA, then what will happen? This ball again that is corresponds to this is the rotational axis along which it is rotating. So, if ZA is negative, then we will have a kind of a fluid attached to the ball as a kind of layer, right, and then rotating without any relative slip, right, and then this bottom of the ball is completely dry and then exposed. So, under such conditions ZA is nothing but negative one. So, negative ZA you can have if the rotational speed is very high, positive ZA you can have if the rotational speed is low to moderate. But in general we know that R omega square is much larger than the G, that is centrifugal force is much larger than the gravity force. The surface is nearly vertical and Z naught has a very large negative value. Thus, in practice the free surface of the liquid will effectively concentric with the walls of the ball. Therefore, the operation of high speed centrifuge is independent of the orientation of the axis of rotation, whether are you rotating along the vertical axis or along the horizontal axis or at some intermediate angle, that is not going to show any kind of effect, because this interface, whatever the liquid interface is there, that is independent of orientation now, because now this layer at high speeds is attached a kind of layer of liquid attached to the walls without any kind of relative slip kind of thing. Okay. So, this is about the shape of the interface in centrifugal field, shape of the interface of a liquid in a centrifugal field, that derivation we have seen. Now, we see the pressure drop, right. What is that pressure in the centrifugal force that is causing the separation to occur, right. So, that we are going to calculate, that is dP by dr is equals to whatever rho r omega square is there, that we are going to derive now. Okay. So, in a rotating centrifuge, a layer of liquid is thrown outward from the axis of rotation and is held against wall of the ball by centrifugal force. Free surface of liquid takes the shape of a paraboloid of revolution. However, in industrial centrifuges, rotational speed is so high and centrifugal force so much greater than the force of gravity that liquid surface is virtually cylindrical and coaxial with the axis of rotation as shown here in this figure. If you have a kind of a very high rotational speed, right, this is the ball, actually this is the wall of the ball, right. So, which is having a kind of a height B and then radius R2. This is the central axis of the ball, right. The radius of this ball is R2. If you rotate this one at very high speed, having the liquid already present in the ball, when you rotate at very high speeds, the liquid is usually thrown outward toward the ball and then almost concentric cylindrical interface you can see here as shown in the picture. And then this is going to be very true, very often occurs in many of the industrial centrifuges that often applied for a given separation, solid separations. Radial distance from axis of rotation to the free liquid surface is R1. So, let us say initially liquid is there. So, that liquid is kind of having this thrown towards a kind of wall. So, like this, right. So, towards the center of this ball we have a kind of empty column kind of thing without any liquid, and then liquid is thrown towards the wall which is forming a kind of concentric interface like this. So, this is this part, whatever this filled part that I am showing is empty, there is no liquid kind of thing. So, that is the radius of the interface, free liquid surface, whatever this is the liquid that is thrown here, and then liquid is now occupied from R1 to R2, that is this is R2 minus R1 is nothing but the thickness of the liquid that is forming as a kind of layer along the surface, and then this interface whatever is the liquid interface is there, that radial distance from the axis of rotation to the free liquid surface is nothing but R1. Radius of the centrifugal ball is R2. Entire mass of a liquid is rotating as a rigid body with no sliding of one layer of liquid over another. Then under these conditions pressure distribution can be found from static principles. Okay. Now, consider a ring of liquid. Now, within this liquid layer, it is actually both sides is there. So, within this liquid layer what you do, you take a layer of liquid or a ring of liquid, we cannot say layer because now it is the centrifugal ball, entire ball surface is attached with a liquid layer, okay, forming a kind of static liquid without any sliding of liquid layer, one liquid layer over another liquid, those kind of things are not there. So, it is a centrifugal ball rotating very high speed. So, within that liquid which is being attached to the ball surface, on that ball surface or that liquid layer, what you do, you take a ring of having thickness dr at distance r from the axis of rotation. From the axis of rotation at distance r, you take a ring of liquid of thickness dr, and then consider mass of that liquid in that ring of liquid is dm. So, then volume of element at thickness dr at radius of r is you can calculate. So, the centrifugal force for that ring of liquid would be nothing but dF is equals to r omega square dm. So, r omega square is nothing but the centrifugal acceleration, right, gravitational acceleration or acceleration due to gravity g is there, acceleration due to centrifugal force whatever is there, that is r omega square. If that if multiplied by the mass, then you will get the centrifugal force, you get centrifugal force, but that we are doing now for a layer of the liquid or the ring of a liquid having the thickness dr. So, in that within this layer of ring of liquid having layer thickness dr. So, the centrifugal force dF, that should be r omega square multiplied by dm, where dm is nothing but the mass of the liquid present in that ring of thickness dr. Okay. So, centrifugal force dF is equals to r omega square dm, but if the density of the liquid is constant and then breadth or height of the ring is given as same as the height of the ball b, then mass of the liquid dm is nothing but whatever the volume of that particular ring of liquid multiplied by the density of the liquid. Then volume of that particular ring of thickness dr is nothing but 2 pi rb multiplied by dr, and then if you multiply this one if you multiply this one by the density, then you will get the mass of the liquid in that ring of the liquid. So, that is dm is equals to 2 pi rb dr rho. So, now this dm you can substitute here in this equation. When you substitute, you will get df is equals to 2 pi rho b omega square r square dr. Now, the force is there. If you divide by the area, then you will get the pressure. So, the pressure due to the centrifugal force that you can obtain now. So, change in pressure over the element in the force exerted by the element of liquid divided by the area of the ring, then we will get dP. So, dP is equals to dF by area of the ring. Area of the ring is what? 2 pi rb. 2 pi rb. So, that is nothing but now what dF we already got it. If you divide that dF by 2 pi rb, then you will get dP is equals to omega square rho r dr. Or from here we can write dP by dr is equals to rho r omega square, right. So, let us say pressure drop over the entire ring is P2 minus P1, then you integrate this right hand side and then substitute ring size R1 to R2, then we will get P2 minus P1 is equals to omega square rho R2 square minus R1 square. R2 is nothing but ball radius, and then R1 is nothing but the radius of the interface. So, P2 minus P1, P2 is nothing but pressure at the ball wall, and then P1 is nothing but pressure at the liquid free surface which is at R1 distance from the axis of rotation. Okay. So, that is P2 minus P1 is equals to rho omega square R2 square minus R1 square by 2. Remember, this equation applies only when R1 and R2 are not greatly different from each other, that is the liquid layer thickness whatever that is attaching to the centrifugal board because of the centrifugal field is not very thick, it is thin. So, that R2 and R1 are not different from each other, because R2 minus R1 is nothing but the thickness of that liquid. But for practical system, the error is so small that you do not need to worry about this R1 and R2 differences, how much are different from each other, because practically when you apply high centrifugal field, this difference in R1 R2 is going to be play a kind of very less influence. So, now using this centrifugal field, how to do the separation of immiscible liquids of different densities. Let us say you have immiscible liquids, light liquid and then heavy liquid, right, and then there may be, let us say, some small solids also. Forget about the solids, we do not need to worry as of now. Okay. So, when you do the separation of these immiscible liquids by the gravity, it will take very long time, and then after very long time, this heavier liquid will be forming as a kind of bottom layer, and then on to top one light liquid will be forming as a kind of a light liquid layer, so that they can be separated out. But here it is going to take long time, because in general in immiscible liquids, though the densities are different, but the difference in densities of heavier and then lighter liquids is not very high, in general that is the case. Let us say the example of obtaining edible oil from vegetable seeds, then whatever the aqueous and oil phases that we get, their densities are in general, oil phase may be having 0.95 gram per cc, and then aqueous phase may be having 0.98 or 1.00 gram per cc, something like that. They are very close to each other, right. Under such conditions, if the densities are close and then forming immiscible phases, settling of those immiscible liquids into two separate layers by gravity is going to take very long time, But if you take a kind of a centrifugal ball, and then in that one you take these immiscible liquids and then rotate that centrifugal ball at high speeds, then what happens, like in the whatever the heavier phase is there or heavier liquid is there, that will be attached, that will be thrown towards the wall and then form a kind of layer A like shown here, and then next to that one the lighter liquid shown as a zone B, that will be attached very next to this heavier liquid, and then from this one, from the top, heavier liquid can be taken from this outlet 1, and then lighter liquid can be taken from this outlet too, right. So, here the notations are again same. R2 is a kind of radius of the ball, and then height of the ball is B, let us say, right. Now, this RA and RB are the corresponding radius of this outlet for a heavy liquid collection and then light liquid collection respectively. Now, because the feed is continuously coming in and continuously you can take out these things, so that you do this process continuously, right. The interface between this heavy liquid and then light liquid, whatever is there, that is RI, and then this RI is a kind of very important calculation. This RI calculation, based on that one, this RA and then RB locations are set, so that the collection of this heavy and light liquids can be taken continuously. So, what is that RI? RI is known as the neutral zone. Neutral zone, A is a kind of heavy liquid zone, B is a kind of light liquid zone, and then in between that interface is whatever is there, that is RI, having the radius RI, which is known as the neutral zone. So, that RI we are going to calculate now. Okay. So, in this process, if at all some solids are there, they will be a kind of settled at the bottom, and then few solids may be climbing towards the corner of the wall like this, that is also possible. So, if at all solids are there, one has to be careful while rotating this ball. So, that is at what speed one has to rotate this ball, that one has to be careful, because if it is rotating too high, very high speeds, then this particle will also be coming towards the ball. We do not want that high velocity, we want those particles to be at the bottom only. Okay. So, because this particles density is going to be much higher than the density of a heavier liquid. So, that one we have to be careful. Anyway, with this particular thing, when there are particles are also there, that we are going to take in a kind of next lecture. Okay. So, as of now, forget about this particles, solid particles in this case. If difference between densities of two liquids is small, gravitational force may be too weak to separate liquids in reasonable time. Thus, separation may be improved in a liquid-liquid centrifuge or centrifugal decanter as shown above in this picture. So, liquid-liquid centrifuge consists of a cylindrical metal ball usually mounted vertically that rotates about its axis at high speed. When ball is at rest and contains a quantity of two immiscible liquids of differing densities, then heavy liquid forms a layer on the floor of the ball beneath a layer of light liquid. On rotating the ball, heavy liquid forms a layer denoted as zone A next to the inside wall of the ball, and then layer of light liquid denoted as zone B forms inside layer of the heavy liquid. Then how to obtain the radius of neutral zone? The cylindrical interface of radius Ri, which separates these two layers which are forming zone A and zone B, that known is a kind of a neutral zone. So, that Ri we have to calculate. Since force of gravity can be neglected in comparison with the greater centrifugal force, this interface is vertical and is called as a kind of a neutral zone. Okay. So, if the density of heavy liquid is rho A and then overflows at radius Ra. So, there is a overflow opening at the top for this heavy liquid to go out, and then radius of that overflow distance, that Ra distance is there from the central axis. That is, this Ra is a location of overflow ducts from where from the top heavy liquid is taken. Rb is the location of the distance from central axis to the location of overflow for a lighter liquid. Okay. Similarly, density of light liquid is rho b and leaves the centrifuge at Rb. If both liquids rotate with the ball and friction is negligible, pressure difference in light liquid between Rb and Ra must equal that in heavy liquid between Ra and then Ra. This is the reason, because we need to know the pressure distribution in centrifugal field in order to get these calculations. What we have done, we have previously derived dP by dr is equals to rho omega square r. Okay. So, therefore, in order to have this neutral zone to be stable, this Pi minus Pb should be equals to Pi minus Pa, where Pi is nothing but the pressure at the interface or at neutral zone. Pa and Pb are nothing but the pressure in the zone A and zone B respectively. So, from centrifugal pressure distribution principles, we have already seen that dP by dr is equals to rho omega square r. When you integrate them, then we have P1 minus P2 is equals to omega square rho r1 square minus r2 square by 2, that is what we have. So, that principle if you apply here, Pi minus Pb should be rho b omega square Ri square minus Rb square by 2, and then Pi minus Pa should be rho a omega square Ri square minus Ra square by 2. So, but these two things are equal at the neutral zone, these two quantities. So, then when we equate these equations, you will get rho b multiplied by Ri square minus Rb square is equals to rho a multiplied by Ri square minus Ra square. So, when you solve this equation for Ri, we will get Ri is equals to square root of Ra square minus rho b by rho a Rb square divided by 1 minus rho b by rho a. So, now we can see rho b by rho a, that the density ratio of light to heavy liquid is going to play a kind of very vital role in positioning this Ri. So, above equation shows that the radius of neutral zone is sensitive to density ratio, especially when this ratio is nearly unit. If it is like almost close to 1, so then this value is going to be, denominator 1 is going to be close to the 0, then it is going to be a kind of very large value, and then under such condition this Ri is going to be unstable. If densities of fluids are too alike, then neutral zone may be unstable even if speed of rotation is sufficient to separate liquids quickly. Okay. Difference between densities should not be less than approximately 3% of so that to have a kind of stable operation. So, equation of Ri, from there what we can understand, if Rb is held constant and Ra is increased, then neutral zone is shifted towards wall of the ball, and if Ra is decreased by keeping Rb is constant, then neutral zone has to be shifted towards the axis. So, this is the importance of calculation of Ri. Based on the Ri value, right, one can change the locations of Ra and then Rb locations, right, so that we can have the effective and then clear separation of these two phases. Similarly, if Ra is held constant, then Rb is increased, so that neutral zone shifts towards the axis, and then decrease in Rb by keeping Ra constant causes a shift of neutral zone towards the wall. Okay. So, according to this value of Ri, one can place this Rb and then Ra locations, so that the separation of these two phases can be taken effectively and continuously. Therefore, practically position of neutral zone is very, very important. That is the reason we have calculated what is this Ri. In zone A, the lighter liquid is being removed from a mass of heavier liquid, and in zone B, heavy liquid is being removed from a mass of light liquid. If one of the process is more difficult than the other, more time should be provided for more difficult step. Let us say if separation in zone B is more difficult than that in zone A, then zone B should be large, so that more time is there for the liquid to separate, and then zone A has to be small. Okay. That is the advantage of knowing this Ri information. This is accompanied by moving the neutral zone toward wall by increasing Ra or decreasing Rb accordingly as per the requirement. To obtain a large time factor in zone A, opposite adjustment should be made, that is moving the neutral zone towards the axis of rotation and then decreasing Ra and then increasing Rb. So, the opposite one has to be followed. Okay. Many centrifugal separators are so constructed that either Ra or Rb can be varied to control position of the neutral zone as well. So, now we see a few centrifugal decanters, equipment that are used for separation of immiscible liquids, or separation of immiscible liquids and solids from a mixture of solids and immiscible liquids. There are several types of decanters or centrifugal decanters are available. What are they? Some of the industrially famous one we are going to discuss now. In industries, immiscible liquids can be effectively separated in centrifugal decanters. Separating centrifugal force is much larger than that of gravity. That is the reason centrifugal force are in general applied so that to do this separation of immiscible liquids. This force acts in the direction away from the axis of rotation instead of downward toward the bottom of the equipment as the gravity does. There are two main types of centrifugal decanters, tubular centrifuges and then disc centrifuges. So, let us start with the tubular centrifuge. In this tubular centrifuge, actually a kind of a tall and narrow ball we have. The ball is having diameter 100 to 150 mm. This ball is rotating by vertical axis like this. The feed is coming here continuously like this and then given in this one. So, then when this feed is having immiscible liquids, then whatever the heavier liquid is there, that will be thrown towards the wall and then collected from this heavier liquid duct or weir. So, lighter liquid is towards this interface of a heavier liquid not towards the wall of the liquid. So, from there there is a weir that is connecting to collect the lighter liquid. That is the basic principle, and then this ball whatever that we are having, that is rotating at high speed. Actually this is the ball and then this is present in this a kind of casing like this. Okay. So, this heavy liquid side wear whatever is there, that can be removable and then can be adjusted as per the requirement. So, whether it is tubular centrifuge or disc centrifuge, whatever it is there, the working principle is same. The design, how the centrifugation is done, how the collection of these heavier and then lighter phases has been done, that is the only difference from one design to the other design. Okay. So, here in tubular centrifuge, ball is tall and narrow, having the diameter in general 100 to 150 mm only, and turns in a stationary casing at about 15,000 rpm. It rotates at very high speeds. Feed enters from a stationary nozzle inserted through an opening in the bottom of the ball. It separates into two concentric layers of liquid inside the ball. Lighter layer spills over a weir at the top of the ball. It is thrown outward into a stationary discharge cover and from there to a spout. Heavy liquid flows over another weir into a separate cover and discharge spout. Weir over which heavy liquid flows is removable and may be replaced with another having an opening of different size. Position of liquid-liquid interface, that is neutral zone, is maintained by the hydraulic balance. This is about the tubular centrifuge. Now, disc centrifuge, here the working principle is same. Again we have a ball in which we take the feed and then rotate it so that feed separates into the two phases, heavy and then lighter liquid phases like that. But within the ball what we are having some kind of a conical sheets kind of discs are there, right. So, towards the center and then or towards the wall of this or towards the edge as well as towards the center of this sheets, there are kind of holes through which these these channels are, these holes forms a kind of channel so that liquid pass from one sheet to the other sheet kind of thing. Okay. So, it is highly effective for liquid separations. It is a short and wide ball of 200 to 500 mm in diameter which turns on a vertical axis. The ball has a flat bottom and conical top as shown here in the picture. Feed enters from above through a stationary pipe set into neck of the ball. Two liquid layers formed as in tubular centrifuge and flow over adjustable dams into separate discharge spouts. Okay. So, there is a light liquid discharge spout and then heavy liquid discharge spout is there. Okay. So, here there are closely spaced discs inside the ball and rotating with it, which are actually cones of sheet metal set one above the other. There are n number of conical metal sheets kind of thing are there, which are used as a kind of disc, and they are spaced very close to each other, and this set is there inside the ball. Matching holes in disc about the halfway between the axis and wall of the ball form channels through which the liquid passes from one disc to the other disc, or from the space between two discs to the next space between another subsequent two discs, like that. Feed enters the ball at bottom and flows into channels and upward past the disc. Heavier liquid is thrown outward, displacing lighter liquid toward the center of the ball. While being thrown outward, this heavy liquid very soon strikes the underside of a disc and flows beneath it to periphery of a ball without encountering any light liquid. Similarly, light liquid flows inward and then upward over upper surface of the disc. Because of the having this disc, what happens, these liquids, they are moving in two different directions. The heavier liquid is moving towards the wall, and then lighter liquid is moving towards the axis of the ball. So, then because of that movement, there is a kind of a friction also. Since discs are closely spaced, distance a drop of either liquid must travel to escape from other phase is much shorter than in comparatively thick liquid layers in a tubular centrifuge. In addition, in disc machine there is considerable shearing at liquid-liquid interface, as one phase flows in one direction and other phase in opposite direction. Because of this one, it helps shearing, whatever the shearing is there, it helps break certain types of emulsions, if at all they are existing in the feed system. Disc centrifuges are particularly valuable where purpose of centrifuge is not complete separation only, but concentration of one fluid phase, as in the separation of cream from milk and concentration of rubber, latex, etc. Let us say sometimes if you have a solid impurities, in the feed, whatever the feed, that immiscible liquids that you are separating, in that feed if you have a solid impurities, then how to clean up in centrifuges. So, whatever the disc centrifuge is there, that can be modified so that these solids can also be removed. However, before that, what we need to know, if liquid fed to disc or tubular centrifuge contains dirt or other heavy solid particles, solids accumulate inside the ball and periodically must be discharged. Okay. This is accomplished by stopping the machine, removing and opening ball and scraping out its load of solids, that is one way. But this becomes uneconomical if the solids are more than a few percent of the solids. You cannot afford to have a kind of interrupting the process, especially in industry level. And then if the solids percent is very high, then you are forced to stop the process and then do the separation. So, that is not going to be economical. Tubular and disc centrifuges are used to advantage for removing traces of solids from lubricating oil, processed liquids, ink and beverages that must be perfectly clean. They can take out gelatinous slimy solids that would quickly plug a filter. Usually they clarify a single liquid in a ball provided with but a single liquid overflow. However, they also may throw down solids while simultaneously separating two liquid phases. How it is being done, that we see now. Nozzle discharge centrifuge, it is nothing but a modification of a disc centrifuge, that we are going to see how it looks like. It is like, pictorially if you see, it is almost like similar kind of a disc centrifuge, but at the bottom there is a kind of a provision to collect the solids. If feed liquid contains more than a few percent of solids, some means must be provided for discharging solids automatically as shown in picture. This is a modified disc type centrifuge with a double conical ball. Okay. So, in periphery of ball at its maximum diameter is a set of small holes or nozzles around 3 mm in diameter. So, at these peripheries what we have are nozzles. We have a kind of nozzles of a very small size like 3 mm in diameter, something like that. Central part of ball operates in the same way as usual disc centrifuge, overflowing either one or two streams of clarified liquid. So, solids are thrown to the periphery of ball and escape continuously through the nozzles together with considerable liquid also. In some designs, part of the slurry discharged from the nozzles is recycled through the ball to increase its concentration of solids. Wash liquids may also be introduced into the ball for displacement of washing as well. So, this through the nozzle not only the solids are being discharged, some amount of liquid is also being collected out, being taken out. So, what happens, this liquid, if you want like a dry solids kind of thing, this liquid has to be drained off. So, further what you can do, you can take this concentrated solid sludge again and throw inside this vessel to further separation of liquid can be taken place. A kind of recycling can be done. In other designs, nozzles are closed most of the time by plugs or valves that open periodically to discharge a moderately concentrated slurry. So, this is about the several types of centrifugal decanters. The references, we have several references for this lecture, but primarily the lecture, the notes that has been prepared for this lecture can be taken, can be found in this first book, Unit Operations of Chemical Engineering by McCabe, Smith and Harriet. So, this reference is a kind of very important reference. Thank you.